Hello, today I am working on LeetCode 589. This is a continuation of tree traversals, and I am doing it iteratively, but doing it iteratively is a simulation of the actual call stack. You're implementing it yourself, okay? So the backbone is of this problem is still recursive. So here's the recursive code. So in this function, you come to the preorder, you print its own self, and then call all of its children and go home. Now, it's uh, in the real world, how this would work is you would push this function on the stack, print it, leave the function, put a return pointer here. After you're done with that subtree, you will come back here, and after you're at return pointer 1 here, and then call this. You leave this function, finish the execution of that, come back to return pointer, sorry, do not label them nicely. Return pointer 2, come back here, call this child, leave the function, come back here until you return at the very end and you exit. So what in this case, since we don't really need to do all this, if we are a little smart about this, we can skip all these return pointers and just you know, push all the children on some kind of a stack and leave this. I'm never returning to this as long as I keep track of what children to call. So that's the idea of, so I'm going to have a stack. I'm going to call this the call stack. So this is not like the call stack in your actual call because that has return pointers. We don't. So, but still I'm calling this a call stack. And what else do I need? I forgot. Hold on, let me have a peek at my code. Oh, no, nothing special. So yeah, in the call stack, when we go through this, so we push one onto the stack first. So let's go through the process since I don't have too many nodes. In this implementation, one being on the stack means I need to start the function, okay? My pointer is over here. Being on the stack means start the function. So let's pop it off and start the function on this. I'm gonna pop that off and start the function. Let me have a pointer here, current. Okay, that's gonna hold whatever I'm working on. Okay, so what do? We first print the self and get rid of the one. Okay, we printed self. I don't need to keep track of this anymore. I just need to keep track of the children. Okay, I'm never coming back to this function again. So I'm gonna put all its children over here. So let me put the children. If I put 3 to 4, the issue is if I push the children from left to right, I will be processing in since I'm trying to simulate a call stack, I will always be working here, right? I will be working on the right child first. So that's why I want to do it in reverse so that I can work on the left child first, as is the case. So we are going root and then left to right. That's how we want it. So let us put the left child on the very top of the stack and the right child at the very bottom. Okay. So we are gonna go reverse on this list. So we are gonna push on the stack 4, 2, 3. Okay. Now, and this I give it to the garbage collector to eat. I'm done. Now this I'm gonna pop from the stack. Let me pop from the stack. I'm working on 3 right now. What does it mean to work on 3? I print itself. I just printed it. I don't need to record itself on, I don't need to record 3 on any stacks because I'm never coming back to 3, but I need to record the children in reverse order. Let's print 6. I don't want them to overlap. Here is a 6. Here is a 5. Again, I am pushing them on the stack in this order so that I can pop them out, process them on that order. Okay. Okay. So I'm done with 3. It garbage collector. It's 3, and now I have a 5. I'm working on 5. What does it mean to work on 5? It means to print 5, push its children on the stack, null, null, null. There are a bunch of nulls, and then they all get popped off the stack. Nothing happens, right? And then this actual node gets popped off the stack. We are processing this now. What does it mean to process this? We print it. We push a bunch of nulls. We pop a bunch of nulls, and then we pop that over. Now we are printing this. So let's print the 2. We printed the 2. And garbage collector is that. And yeah, and then also there was a bunch of children null. Okay, I forgot to do that, but you get the idea. I'm copying over the 4, or popping the 4 from the stack, processing this. What does it mean to process? It means to print yourself and push all your children. I push a bunch of null, the nulls get off, and the stack is empty. So my stopping condition would be until my call stack is empty, and I will start with the root over here so that that's my call. So this is the way to be on the stack in this implementation means start the call. Okay, start the function call. You start at the very beginning, you print and push all the children, and you forget about whatever you just processed. Okay, that will be held in your list. And this is the right answer. So let me go to the code and discuss my implementation. Uh, and as you can see, 135624, I'm gonna return 135624. So we are processing it correctly. Okay, so let me explain my code. This is okay. So I made a couple of improvements to improve the performance. Again, I'm not focused on performance here. I'm focused on understanding the problem. ChatGPT suggested I use an array list instead of a linked list, and the deck class as a stack instead of the stack, because the stack is um, that's synchronized, so that adds a little overhead. Array lists are more efficient in the way we are using them, appending to the list. So that's why I'm using array lists. Okay, those are but initially I had a stack over here and the linked list over here, but these are some efficiency stuff. And then this root, again, if there is no tree, we return a blank list. That's a no-brainer. Now we start our function with this. We push the root on the call stack. Now in our implementation, being on the call stack means we have to process this. Current node is currently nothing, it's set to null. Now this is my condition is as long as there are calls I have to process, okay? So current is I pop stuff of the stack. So current is right now the root. And then I go through, I print itself and then add all its children to the call stack. Now I do that in reverse order. It is int I current dot children dot size -1. So that's the last index of the children up to 0 and I minus minus. So it goes from the end of the list to the very first index of the list, which is 0, and then it pushes all those children with get I, and then you return the result. Now, I'm just going to explain this comment. This comment, I was trying to use iterators to reverse the list because I was not sure that the list they provided, huh, why did I try to use the iterator? Oh, the list of children. Right, this list of children, I don't know if they're a linked list or an array list. Because if they are an array list, get would be fast because it's you don't have to go through all the previous children, it's O of 1. But if this was a linked list, this would be O of n. But it turns out probably they gave me an array list because this turned out to be slower. Anyways, that's some silly talk. Okay, so this runs, let me submit. My submission will not be super good, but I'm happy with it. I understand the code, I can explain it. I might try to pursue this by doing a recursive call. Maybe there are some optimizations would make it faster. Anyways, that concludes my presentation. If you have any questions, please leave them in the comments, and I hope you have a lovely day. Bye-bye.